Good morning. Let's continue on the welded joints design. Okay, so last lecture we had an introduction on welded joints, mainly on symbols, right? The type of welded joints. So today we'll look at the design for welded joints. Okay. Okay, so first of all, okay, the focus for the welded joint in our case will focus on fillet. Okay, the fillet type of joint. Okay, yeah. But let's look at a couple of terminologies again. Okay, related to the design. So, for example, this is a butt type of joint weld. Okay, this is a butt weld, and this is a fillet weld here. Okay, yeah. So CGP represent completely joint penetration, and PGP represent partial joint penetration. So one of the key parameter in welding or welded joints is this so-called throat here, the T. Okay, the throat. So this T is a key parameter, basically determines the strength of this welded joint. Okay, yeah. If it's a butt weld, the T is fairly easy to determine, and that basically is the thickness, okay, of the member at here. Okay. Now there's always a little bit this so-called reinforcement, okay, portion at here for the welded joint. So basically a little bit extrusion at here. Okay, so that's called reinforcement. And same thing for fillet weld here. So you have a little bit extrusion in here. Okay. And the other important parameter here, as it says here, the fusion area. So the fusion area refers to the basically attachment area, right, between the fillet and the base metal. Okay. Yeah. So for the fusion area, so for this one here, the fillet here is a triangle. So the length of the vertical side of the triangle is called the leg. So okay, so the leg here. So I use the W, but we generally will use H in our class at here. Okay, so basically, if this is the fillet at here, then this is H. Okay, so both sides is the same H at here. Okay, then the throat. Okay, then the throat at here is basically the distance. Okay, the vertical distance from here to the hypotenuse. Okay, so this is a T at here. Okay, this is a T. And typically, this is a right triangle equal sided, so it's a 45 degree. Okay, yeah. So if you know the H, then you'll be able to calculate this T. Okay, this T. So the T basically will determine this is so-called throat area. Okay, this so-called throat area. So the throat area is basically the T. So you can imagine. If you cut, right? If you cut it like this, and you cut into it, and it depends on how long this the member is, right? Then you have a length basically. So then T times the length, okay, is this throat area. Okay, yeah. So the length L generally you can't change, but it's the T, right, will determine this throat area, and this throat area ultimately relates to the strength of these welded joints. All right, yeah. So another terminology, like for example, we call this a toe, and this is a face, you know, something like that. Okay, this is a root. Okay, so just know the meaning of these ones here, and that should be fine. So the fusion area, if you look at the fusion area, let's see, the fusion area basically refers to the size that is here, right? You can basically calculate also easily if it's a fusion area. So apparently it's H, then times L, right, for one side here. Okay. Yeah. Okay. So talking about the strain, the design of or design analysis of welded joints. So basically, we're back to our general practice. We need to figure out what is what kind of stress, right, or how much stress exists at these welded joints, and also how do we determine the strengths, okay, for these welded joints. And then we compare each other, so then we get safety factor or design, right? We get certain parameters. So the first the first topic that we're going to look at is we'll look at basically so-called the shear stress. Then we'll explain why we just see the shear stress, okay, on weld, okay, and welded joints. Okay, yeah. So first of all, let's look at a very simple case, the butt weld. Okay, if you have a butt weld like this case that here, okay, like this case. So you can draw the butt weld. Let's say if you have a force, if you apply the force on the two sides of this, right, on two sides here, okay, then the stress at this joint at here, yeah, it's not exactly going to be a shear stress, but okay, yep. So I'll just write the butt type, okay. Okay, so if you have a plate, you know, the drawing is not that great, but you know what I'm saying here. If you have force at here, so for this type, then you have a sigma is F over A, right? F over A. So the A at here, what we do is we take the A as the throat area. So that's which is basically it's H times or T times L, right? Depends on how you define. Let's say if they define as H at here, then it's basically if you use a T at the beginning, you can see that's the same as F over HL. Okay? Yeah. So this is the loading. If the loading is this way, now if the loading, right? If you're loading it, okay, like this. So basically, if the weld is like this, then if you load F, it's in this direction, okay? It's in this direction. Then now this time you have a shear stress now, right? It's still F over A, and it's still F over basically HL. Okay, that's butt weld. Okay? Yeah. Is that good? So as I said, the focus is on fillet. So now let's look at the fillet type of weld. Okay, let's look at the fillet welds. Okay. So for fillet weld, let's look at a double lapped joint here. Basically, I have 3 plates. Okay, so we're welding the 3 plates together with a fillet weld. One is here, the other is here. Okay, yeah. Now we apply the force, the loading. Let's say this is F over here, and this is 2F. Okay, incredibly ring. Okay, yeah. So if this is H, so well, I guess I should probably write it more precisely. Let's see, H is this. Okay, so leg size is H. Okay, so leg size H. And the throat is basically, as we defined, it's the vertical distance, right, from here to there, right? So basically, the throat, that's the T, throat. Okay, so this is the welded joints with the fillet type of weld, and let's look at what kind of stress exists in this fillet weld here. Okay, so what do we do is first let's do a so-called theoretical calculation. Okay, unfortunately we are actually not going to stick to the theoretical calculation, but we need to use the results of theoretical calculation to justify what we're going to use. Okay, so what we do is let's cut a cross section. Okay, let's cut a cross section at this fillet weld that are here. Okay, so when we cut a cross section, basically we cut it at arbitrary angle. Okay, so not necessarily 45 degree. It's basically arbitrary angle. So then if I single out, so this is my next diagram here. If I single out the top portion there, and this is what you're gonna see. Okay, so actually not this guy. This is for later. move it further down there. Okay, so if I cut it, so let's see if I'm going to look at just the top one here, and where do we cut? We cut it basically at something like this. Alright, so this is a theta, right? This is a theta. Okay. Okay, yeah. And this is the F over here. Okay. Now, you cut it here. This piece should still be in equilibrium. Then, at this cutting cross section at here, right? Then we should have probably, let's say, two forces. One is this way. Let's call it Fs, and the other one is this way. Let's call it Fn. Okay. So altogether, the three forces should still maintain this piece in equilibrium, right? Okay, yeah, that's the idea. Okay, then basically the idea is let's calculate this Fs will cause a shear stress, and this Fn will cause a normal stress, right, on this cross section at here. Okay, yeah. So how much stress will it cause? Then that really depends on the total area of this cross section at here, right? Yeah. So let's call this A, okay, as this so-called shear area. Okay, so this is the area here. Okay, yeah. If you extend that, basically, imagine that if you extend it beyond to the other side, right? So that basically is the A. Then let's say the total length is L. Okay, total length is L. So if total length is L, all we need is what? All we need is the this portion of a length, right? And then times L, that'll be the A. That makes sense, right? Yeah. So here you need to use a little bit of high school basically geometry now. So if I draw it like this, okay? This is a theta. This is H. And the top angle here, see this angle here, right, is basically that angle there. And that angle, remember we said, is generally how much? 45 degree, right? It's 45 degree. Okay? Yeah. So now you can use this so-called sine rule. Okay? So sine rule basically says H over the what do you call this angle? The angle on the opposite side of this H. So, and how much is that angle? That angle is what? 180 minus 45 minus theta degree, right? And then equal to this side here. Let's call this is H star. Let me call it T star maybe. Okay, like T star. So that basically is a T star over how much? Sine 45 degree, right? Yeah. So then you can solve for the T star in terms of H and the theta. Is that all right? Yeah. So then the T star you can solve, which equal to basically equal to H over cosine theta plus sine theta. You get this. Okay. Yeah. So then the shear area, the A, will equal to what? The T star times L. So that's H over cosine theta plus sine theta times L. Okay, that's your shear area. Okay, so the area A depends on how much angle that you cut, right? Like that. Okay. Is that good? Yeah. Okay, so then because equilibrium, then how much force is Fs and how much force is Fn then? So that's basically equilibrium equation. So Fs should equal to F sine theta and Fn should equal to F cosine theta. Alright, so now you have the area, you have the two forces, then we're able to calculate the shear stress and normal stress at this cutting cross section. Okay? Yeah. So shear stress. Tau equal to Fs over A. Okay, so that's which is F sine theta cosine theta plus sine theta square and over HL. Okay? Yeah. And normal stress is Fn over A, which is F, okay, sine theta cosine theta plus cosine theta square and over HL. Okay, so that's the two stresses, right? That's the two stresses like that. Is that good? Yeah. So, as if you recall that in the at the beginning of the course, we learned a review on the state of the stress and analyze, and also we learned the distortion energy theory. So let's say we're gonna do this. Okay, we're gonna take a little bit the stress element, okay, out of that location, right? So if I take a stress element out of the location, then what am I looking at now? Let's see. I'm gonna move this down a little bit here. Okay, so basically, if a stress element like that, okay, then you have shear stress, basically. Then you have, okay, a sigma. Okay, so basically you have a sigma x and you have a tau xy. Okay, it's a plane state of stress. Okay, the plane state of stress. So the sigma x right here is this sigma, and the tau xy there is the tau we just derived there. Okay, yeah. So then I can calculate von Mises stress, which is sigma square plus 3 tau and 1 over 2 square root. Okay, so basically plugging these quantities over here, we can calculate sigma prime. Okay, yeah. Okay, so now the purpose is doing the following now. We have the two situations now, so you have a sigma prime. So apparently, see, sigma prime is what? It's a function of a theta, right? It's a function of theta. So the question here is, at what angle of a theta would you have the maximum von Mises stress sigma prime? So what would you do? You take the first derivative, right, over theta, and then you set it equal to 0. Okay, and you solve for the theta angle. Okay, that's called the stationary point, and you get the angle is 62.5 degree. At this angle, and we get the sigma prime, which is the maximum, equal to 2.16 F over HL. Okay, over HL. And at this angle, you can substitute this sigma angle back into tau and sigma. Okay, back into tau and sigma. So we get basically, okay, at this angle, we get the sigma equal to 0.623 F, okay, over HL, and tau equal to 1.196 F, okay, over HL. Okay, so this is so-called basically theoretical calculation of the maximum. Is that good? Yeah. So similarly, you can also do this. I mean, look at this. This is you calculate maximum for von Mises stress. But if I look at the shear stress is also a function of theta. So I guess I can also calculate a maximum of tau, okay, at a certain angle theta, right? Yeah. So if I do this, let's say, basically, if I do d tau over d theta and set equal to 0, we find that at a theta equal to 67.5 degree, we have a maximum for tau max. And this tau max is 1.207 F over HL. Okay, over HL. Okay, yeah. So pretty close, these two. You see, right? The two shear stress, okay, calculated based on the two maximum conditions, they are very close to each other. Okay, yeah. Okay, so having done all of this one here, but as I said, we're actually not going to use this. The reason is because no theoretical value actually matches the actual stresses in practical situation. Okay, So in practical situation, then what do we do then? So people come up with this basically a more so-called more conservative approach, which I'll show you why it is called so conservative. Basically, okay, so the idea is, okay, theoretical, okay, results, okay, not gonna work. Well, I understand not gonna work, but it's just not gonna work for all the cases. So what we do is we use a, let's say, so-called conservative, okay, model. Okay, so this is a conservative model I'm talking about here. Okay, so what's so conservative? We assume there is no normal stress on that cross section. We also basically what we do is we basically explode, okay, the whole force, okay, all on this shear stress at here, okay, and this whole force is on the throat area, okay, 45 degree. So that's the model we're talking about here. Is that good? Yeah. So if this is the case like this, right, basically we explode the total F to that Fs, the shear force, and then we assume this Fs applies to the 45 degree cross section. Okay. Then if this is the case, then how much shear stress do we have then, right? Because this conservative model. So let's look at it. Shear stress equal to F over A, right? Now the A is the cross section at 45 degree. So then how much is A then? A is basically T times L, right? T times L. And T, how much is the T? So this is basically, if you draw the triangle here, this is 45 degree, right? And this is H, this is T. This is 90 degrees. So guess what? The T equal to 70.7 H, right? So square root of 2 over 2, right? So then the total shear area is 707 H times L, okay, times L. Then 1 divided by 0.707 is equal to 1.414 F over HL. So this is the shear stress due to this conservative model. That makes sense? Yeah. So now you can sort of guess why is this conservative now. If you look at this value with the two shear stress that we just calculated, this guy and this guy, which one's bigger? Right? They all have the same F over HL. The coefficients, this is 1.2, 1.2, and this is 1.4, right? Yeah. So this is basically a conservative model. Okay, it's a higher shear stress value than your mathematical calculation of a maximum, basically. Okay, is that good? Yeah. So as a matter of fact, you can also calculate, right, for this conservative model, right, for this model, you can also calculate the von Mises stress. Based on this model, the von Mises stress can be calculated, which is 2.45 F over HL. Okay, and the maximum von Mises from the mathematical model is how much? Is 2.16. So this is still basically, right, larger than that your mathematical maximum. Okay, yeah. So that's why this is a conservative model. Okay, so we're going to use basically this idea. When we look at the stress of a fillet weld, we will only look at the shear stress. Okay, and we will basically only look at the shear stress at which location? At the throat area. Is that clear? Yeah, that's basically the assumption now. Okay, so now let's look at the existence of stresses. Okay, for two different scenarios, right? Yeah. So the first one here is, let's look at let's call it case number 1. I call it shear in the weld, the fillet weld. Okay, from in-plane torsion. Okay, so I'll explain to you what I mean by in-plane torsion at here. Okay, so here's the basically the type of loading and under for the type of welds here. Let's say you have a base metal at here, okay, and you have another plate. Okay. Okay. So we're going to weld the two plates together. So let's say you can weld the two plates together actually using different scenarios, but let's say we're going to weld it like this, So you have a fillet weld at this location, and you have another weld at this location here. All right? Yeah. So typically you would indicate basically using you probably will see a symbol like this, right? So basically symmetric on both sides, okay, and with a certain maybe leg size h equal to something, okay, yeah. And we have a force, okay, loaded at the tip. It's all good? Yeah. So if I look at from the side view, basically if we look at it from this side here, right? So what do we see? We see a plate, and then we see another plate at here, and then we see the welds, right? And then the force is over here. Okay, force over here. Okay, so to get the stress, we need a free body diagram. Okay, free body diagram basically is the free body diagram for this plate at here. Okay, so we look at the plate. Okay, the first of all, the centroid. Let's see, the centroid for this weld group. Okay, is this location. Okay, if this is the centroid for this weld group, okay, then your free body diagram, I'll draw the free body diagram on the bottom here. Okay. You have the force over here, right? You get a force here. So the force will generate a torque around this centroid, okay, or center of mass for the weld group. And you need a reacting moment, right, to counter-react that moment. So basically, you need a moment m in this direction to, okay, cancel that moment from f, and that moment is basically f times this much distance, right? Yeah. At the same time, you also need a shear force, right, to cancel that shear force f, right, the force at this location. So that's the that's basically the free body diagram, right, for this one here. Okay. Yeah. Okay, so then when we come to the existence of stress, so now we're talking about we're talking about the stress that existed or that exists inside the weld. And where do we look at it? We only look at where? The throat area. Okay, again, it's the conservative model, right? Yeah. So if I basically cut a cross section, if I cut a cross section anywhere, just right in front of this location here, okay, right in front of this location. So then, what kind of stress do we see then? Let's see if I pick a location at here, okay. If I pick a location at here, then apparently, what kind of stress is this here? You have an F acting on this location, so you have basically a shear stress, right, due to the F, the shear force. At the same time, you also have this F time at the distance, basically due to this M moment here, you will have what? That's what we call basically bending normal stress, right? If it's a bar, basically. That makes sense? Yeah. And bending normal stress, if you remember, the formula is what? It's M times R over G, right? The formula is M times R over G. So M is not going to change. M is this. And R is the distance from basically the center to wherever you're looking at. So if I look at from center to where I'm looking at, apparently which location has the maximum R now? The corner, right? This corner here. if you connect this to any locations on the weld, you have a distance. That's the R. So this is basically the location that gives you the maximum R. Maximum R will give me maximum stress. Okay? Yeah. So there are basically two types of stress exist in the welded group head here. One is due to the F, the other is due to the M. Is that clear? Yeah. So the location that the particular interest is basically here. Okay? It's this location. Okay. So at this location, how many stress? As I said, there are two different stress. One is a stress due to the F. So this one here, I'm going to call it tau prime. The other stress is due to what? Due to this bending moment. The bending moment also causes stress. What direction is that stress then? You're bending it, right? The direction of stress should be what? It's like you have a torque basically applied over here. The stress should be basically perpendicular, right, to the R at here. So let's call that tau double prime, okay, at that location. Is that good? Okay. Now I'm calling it tau double prime here. Okay. So this is basically, you need to basically be careful here. I will give you the exact definition now for the tau prime and the tau. So tau prime we call the primary shear stress. Okay. So this one basically equal to F over A. Okay. F over A. And A area here is the throat area. Okay. More precisely, you should see the total throat area. Okay. Okay. And the tau double prime, okay, is what we call secondary shear stress. Okay, secondary shear stress due to the moment. Okay, due to this M moment. And how much is tau double prime then? So the tau double prime equals basically M times R over J. Okay, M times R over J. So I'm not calling it bending normal stress. I'm calling it basically, this is what we call we can call the bending shear stress. Okay. So if we consider the shear stress, is that okay? Yeah. It's basically, as I said, the conservative model takes into consideration is everything is a shear stress at the throat area. All right. So that's why we call it the secondary shear stress. Even though the formula, right, it's like the original one is like the calculating bending normal stress, but we still call it a type of shear stress. Okay. Yeah. So now, if I look at this existing stress here, you have a tau prime, you have a tau double prime, right? And what do we need? We need the total shear stress, right? And total stress, shear stress, the addition of the two vectors. That makes sense, right? So basically, you can mathematically you can add these two together, you get the total one, right? Yeah. So, but that's typically not very convenient to calculate like that way there. Okay, it involves a lot more calculation. So what do we do generally when we calculate the total shear stresses? We calculate like this. Okay, so let's say I'll draw the two shear stress over here. So one is this way, and the other is this, right? Yeah. So what do we do is okay, so this is the centroid. Okay, this is the 90 degree there. Okay, we decompose the tau double prime, okay, into the x and y direction like that. So let's call it tau double prime x and tau double prime y like this. Okay, yeah. It really doesn't matter how you tell. You can call this is y, this is x. Which one will be making more sense? Maybe this should be y here because x, y coordinates satisfy a right-hand rule, right? Okay, so you decompose that into the two directions here. Okay, two directions. How do you decompose? I mean, all you need to know is basically the angle, right? The angle here. And the angle can be easily calculated based on the geometry of this welding. Okay, so I'll show you there are different geometries. We don't deal with very complex geometries. So given the geometry, you can calculate. You know, you have to. This has to be perpendicular. You'll be get what's the number of there, right? Yeah. So then your tau total will be what? Will be basically the x component. The x component is tau prime plus tau x double prime square, and then plus tau y double prime square, and then take the square root. So that'll be your total shear stress, right? That'll be total shear stress. That make sense? Yeah. So this is how you calculate the total. Okay. Now coming back to the equation for tau prime and tau double prime. So let's take a look at what will be easily calculated. M, that's easy, right? So mf times the length, that's m. And r, that depends on the geometry. You know, you can also get that r. So what about the a? What about the j? Right? That we need to know that before you calculate tau prime, tau double prime. So j here is the so-called polar moment, okay, of this inertia, okay, group. Okay, polar moment inertia group. The group basically is an area. It's also can be called polar moment of area, basically. Okay, yeah. So mathematically, if you have a certain area, then you can basically calculate the polar moment and area, right? Yeah, you actually learned that previously. So, for example, you know, basically, let's say, what's the basically the inertia group, or I can also say that basically it's the welded area, right? What's the welded area? So you can the welded area here. Okay, you should know that again. This refers to the throat area. Okay, the throat area. So basically, it's the polar moment of the geometry of the throat area. So for example, I'm not going to go into too much details here. Let's say if your welded group is like this. Okay, if your welded group is like that, right? Yeah. So this is there's a weld here, there's a welded here. So what I draw here, okay, what I draw it here, the two rectangles I draw here, are the throat area. Is okay? Yeah. So this one here, right? These two. Let's see. I'll just call it. This is the throat area. Okay, this throat area. If this is the throat area, and if this is the centroid, okay, let's say if this is the centroid of the two area, right? You know, basically the center of mass, but this area there's no mass, so basically that's the centroid here. Okay, yeah. Then the J is basically the polar moment of this total throat area about this centroid. Okay, so if this is the G here, so we're basically looking for what's the JG equal to. All right, yeah. So you can imagine there is a rotational axis going through this G, which is basically perpendicular to the plane, right? And then you calculate basically the JG, right? And the calculating the JG, the mathematical formula is this. So it's a double integral because it's this plane area. So what are we integrating? We're integrating x squared plus y squared, and then a dr. Okay. So that depends on how your x and y axis, let's say maybe your x and y axis is defined over here like this, right? Yeah. So mathematically, that's how you would calculate the JG. Okay? Yeah. So the throat area, if I, to be more precise at here, this one here, this side here is basically the throat length, the T. This one is another T2. So it could have a different T. It depends on the leg size, H, right? Yeah. And this is the total length for the two sides. Okay. Yeah. So I'm not going to ask you to calculate the double integral here. So what we're going to do is we're going to make use of a table from our textbook to facilitate or basically make the calculation faster. So here is the table I'm talking about here. Okay, so this is a table. I'll just take only a portion of the table. It's a table 9-1. Okay, I'll just take one portion of that. Okay, now what does this table tell us is this. This is how you read this table here. Okay. Now, first of all, okay, let's go back to this kind of a generic drawing it here. When you calculate the JG, you basically based on certain T1 and T2. That's the throat length, right? The throat T. But if we set this T1 or T2 as a unit length 1, okay, as a unit length 1, then we are able to generate a table like from table 9-1 at here. Okay, so table 9-1 is basically based on a unit length. Okay, that for the throat area. Okay. Or for the throat width T. Okay, this is the table 9-1 is based on here. Okay, so let's say, for example, right? What do we have here? You have. This is the basically one type of weld. It's like you just have one line of welds, right? If I go back to this drawing it here, it's basically what does it look like? Essentially, it's just one weld at this location, for example, right? Or at this location. That make sense? Yeah. If that's the case, then what is the J value then? So the area, first of all, the area. It's 0.70 h times d. Okay, h times d. So that's actually makes sense because that should be a 0.707 at here, right? Yeah, it's like the 0.70 h times L. But this is the h, so that's the throat area. There's only one, right? It's this. If you look at this one, there are two welds. What's the area now? It's 1.414 h times d. That's the total throat area, right? Yeah. And you also have the average, basically the central location, x bar and the y bar, corresponding to this geometry at here for the welds. That's given on this column here, right? So you need this information. Okay, you need information to calculate the tau double prime. Okay, because the tau double prime, remember, is how much? Is m times r over j, right? So, for example, if this is a weld group here, if we're going to calculate the tau double prime, so apparently this is the location that's particular interest to us, right? Yeah. So then what's the r now? The r is basically what? X bar square plus y bar square and then square root, right? Yeah. So instead of you figure out yourself, you can use the information from the table. J here is called unit second polar moment area. Remember why it is unit? Because the table is generated based on the unit length for the throat width, the T, right? The T. It's set it to 1. Okay? So then the J here is called JU. It's a unit second polar moment of area. Then what would be the actual J then? Right? So the actual J is basically 0.707 h times the JU. Okay? This one is the actual T, right? It's the actual T. So just scale it back, you will get your actual J. That make sense? Yeah. So GU at here is only a unit second pole. You don't use this for your calculation. You have to apply this one first, then you substitute into the moments equation at here to calculate tau double prime. Okay? Yeah. If you're interested, I can show you a couple of examples how the GU is derived, basically purely based on the double integrals, stuff like that, and then you'll be able to get this value here. Okay. So to bring to your attention more is you look at the GU here. What does GU depends on? Depends on the D, depends on the B. They are not arbitrary symbols. They are from your actual weld group geometry. This is the D, this is the B. Is that good? Okay. So if you look at this one here, okay, there's one missing though. What is missing? It doesn't have what I draw it here, right? So what I draw is what? What I draw is not this. When you have this one here, it basically your welding is like it's like this. You weld it here, and then underneath that plate over there, right? That's for that one. But what I draw is you have a weld group like this. Okay, so basically you can use the two line for illustration. So what does that mean? Do we need to recalculate this weld group or not? Do we need to calculate the GU for that? Or we can recycle this? Recycle this, because this is basically rotation, right? Rotation about this G at here, and it's incline rotation. So if the geometry is the same thing, the G value you calculate will be the same thing. Okay, but then you got to be careful now. So basically, you need to, if you want to recycle this one here, okay? So then you need to know that this is going to be your B, and this is going to be what? The D value. Okay, the D. Okay. So if the question give you is this group here, if the question tells you certain dimension, then you need to know what is B, what is the D, so then you can calculate the GU. That make sense? Yeah. So otherwise, you will get the wrong GU, then the rest of the calculation will be wrong, right? Yeah. So just to be careful about this one in here. Okay. Yeah. Similarly, for other shapes like this, if you have a geometry like this, then this is your GU, right? You need to know this is the B, this is D, and the X bar, Y bar, and you also need to know where is the critical location. For example, for this one here, which critical location would you look at? Are you going to look at this location? Or here, or here, or what? Maybe I should look at where? At the edge, right? Yeah. Because that's the location which has the maximum distance from the centroid, right? Yeah, from the centroid. So the question is, what will be the R then? How do you calculate R? You can based on this X bar and Y bar, right, to calculate R. Okay? Yeah. Was that good? So we'll look at more examples in the next lecture. Okay? Yeah.